The Terabyte RAM Bottleneck. MegaETH's sequencer requires a minimum of 1 terabyte of RAM to function. While most Layer 2 protocols fight over data availability costs or proof generation times, this architecture identifies the real enemy as the hard drive. By pulling the entire blockchain state into memory, the protocol eliminates the millisecond delays inherent in solid-state drive seeks, which currently cap the EVM at a few hundred transactions per second. It is a hardware-first bet that assumes the only way to hit 100,000 transactions per second is to stop treating the blockchain like a database and start treating it like a high-frequency trading engine. This shift from disk-based to memory-first execution defines the entire performance envelope for the network. And the way they split these hardware requirements across different nodes is where the engineering gets aggressive. Heterogeneous node specialization. Most blockchains fail because they force every node to be a hero, requiring high-end specs for everyone just to keep the network decentralized. MegaETH breaks this by using a heterogeneous node model. A single, specialized sequencer handles the heavy lifting of transaction ordering and execution on data center-grade hardware, while replica nodes only apply the resulting state updates without re-executing the math. This separation allows the sequencer to push block times below 10 milliseconds without forcing the entire network to upgrade to $4,000 workstations. It is a calculated trade-off. You centralize the execution throughput to gain massive speed while delegating the safety and verification to a much broader pool of participants. However, keeping those lightweight participants in sync requires a fundamental rethink of how state is verified. This leads us to the mechanism of stateless validation, the magic of stateless validation. The primary technical hurdle for any high-speed chain is the state bloat that eventually chokes out honest validators. MegaETH solves this through stateless validation using cryptographic packages called witnesses. Instead of requiring every validator to store the entire history of every account and contract on the network, the sequencer provides a witness for each block. This witness contains only the specific data needed to verify that exact block's transactions. This means a validator can confirm the sequencer isn't cheating using just a few megabytes of data and a standard laptop. It shifts the burden of proof from the entire chain's history to a single point in time. By making verification cheap while execution is expensive, the protocol attempts to solve the scalability trilemma by decoupling hardware power from network security. This design choice fundamentally changes the competitive landscape for EVM-compatible scaling. The signal under the noise. MegaETH's transition to mainnet and the subsequent token launch in April 2026 mark a pivot in the industry from software optimization to hardware limit engineering. By combining the memory-first sequencer with the witness-based stateless validation discussed earlier, the protocol is effectively testing if the EVM can handle the same workloads as centralized cloud providers. This matters for the builder, who is currently forced to move complex logic off-chain because of latency or state access costs. We are seeing the first real-time applications, like the MNSTR collectibles platform and the Euphoria trading engine, move on to this architecture because they require the sub-10 millisecond response times that disk-based rollups cannot provide. For the analyst, the metric to watch isn't just total value locked, but the ratio of complex compute transactions versus simple transfers. This will reveal if the network is actually attracting high-performance applications or if it's just a faster lane for existing DeFi primitives. The next major indicator will be the performance of the Moss wallet as it attempts to manage high-frequency state updates for millions of concurrent users. Subscribe for more.